Hello there, welcome to the first session I'm going to be doing about special relativity. And to start off with, I need to get us into the right, understanding about where special relativity came from and the original ideas. For that, we really need to know our position in space and time. And for that, we need a frame of reference. Now, a frame of reference is in reality a set of axes, three axes, which allow us to locate at any moment an exact position in time and space. Okay, so we know what time it is, and therefore using the x, y and z coordinates we can tell us what location we have in space. And this is fairly straightforward, like okay, I can work out exactly where I am with reference to these axes. We're going to take this a little further now, and I'm going to take you through the thinking which is going to take us to some of the ideas of special relativity. So okay, you're happy with that, you can identify a location in space. All good, we think. We've got a problem. Our first problem is that if you consider yourself stationary and you look at Jackie, you say that Jackie is moving to the right at 90 kilometers per hour. However, from Jackie's point of view, Jackie says actually you're moving to the left at 90 kilometers per hour and she's the one who's stationary. And here is the essence of our issue. The essence of our issue is that motion and all motion is relative. So in spite of our everyday intuition, the only velocities that can actually be measured are relative velocities. So examples here would include the fact relative to the surface of the Earth, but the Earth is moving at 30 kilometers per second around the Sun. We could think about relative to the Sun, but the Sun is moving at 250,000 kilometers per second around our galactic center. Or relative to a distant galaxy, Andromeda is moving towards us at 100 kilometers per second. So how can we actually have a clear reference point when every velocity we're working at is relative to something else? And here's one of the nuances of what we're going to be thinking about now. So in classical mechanics, the velocity of A relative to B is given by this expression. Okay. So the velocity of A relative to B is going to be velocity A minus velocity B, remembering that velocity is a vector, so it's going to have direction as well. And that's fairly straightforward. Okay, so if they're both moving in the same direction, it becomes a fairly straightforward calculation. So let's look at an example of this. Okay, we have a batter who struck the ball at 30 meters per second, and the running outfielder who's running towards the ball at 10 meters per second. So what's the relative velocity of the ball for the running outfielder? Well, using the thinking we've had beforehand, we've got 30 meters per second and we've got plus 10 meters per second. Remember, that's a plus just because it's in the opposite direction. And that means that the ball is approaching her at 40 meters per second. That's the relative velocity of the ball. Okay, so that seems an okay first step. So that is the idea of a relative velocity. Now, what we have now is what's known as a Galilean transformation. So, a mathematical transformation used to relate the space and time variables of two uniformly moving reference systems in non-relativistic kinematics. Okay. What that really means is when an object is not accelerating, okay, so that means two uniformly moving reference systems, so not accelerating systems, then we can use a Galilean transformation to work out the relative velocity between these two frames of reference. What we actually do is, if we have one frame moving at a velocity v with respect to another, then what we find, and we'll try and keep it simple here, so the velocity is just going in a straight line, so therefore we can work out the location with respect to the other frame of reference using these formulas. So if we have an initial frame of reference, and we have a moving frame of reference, then if we know the velocity of the moving frame of reference, and then we can work out locations in this new frame of reference, which is x exclamation, y exclamation, z exclamation, t exclamation, compared to the original positions. Now, if we're moving in a certain direction, therefore t is consistent, z is consistent, and y is consistent. But as we're moving in the x direction, that's where the change takes place. So, here's an example of a Galilean transformation. The elephant sets off at a velocity of 10 meters per second along the beach. What are the coordinates in the elephant's frame of reference? Okay, so the new frame of reference we're doing is with respect to the elephant. What is the starting position on the beach after 2 seconds? So think about the formula we've got to use here. We recognize that the original starting position of x was 0. We recognize that the velocity of the elephant's frame of reference is minus 10 times 2. So that means that the location x in the elephant's frame of reference is now minus 20 meters. So that means the starting point is 20 meters behind where the elephant came from, which makes sense there. And that allows us to see a Galilean transformation. Galilean relativity, so it was Galileo who came up with these ideas, had a principle of relativity, essentially states that regardless of an observer's position or velocity in the universe, all physical laws will appear constant. From this principle it follows that an observer cannot determine either his absolute velocity or direction of travel in space. Okay? So everything will appear similar. And this is the idea is that if you were on a train traveling at a constant velocity and the windows weren't open, and so you couldn't see outside, there'd be no way of working out if you're moving or not. And that's Galilean relativity. This leads towards, and this is the stepping stone towards the special theory of relativity. We'll talk about that in more detail here, but if all motion is relative, not to any stationary hitching point in the universe, but arbitrary to frames of reference, then we have this situation, as I've just mentioned, looking at the train, and that would never be able to work out if the train was moving over uniform velocity or at rest. And when we start thinking about objects traveling at the speed of light, this becomes interesting. So this is the starting point for the special theory of relativity. We're looking at the classical mechanical ideas, so that's Galilean transformations and frames of reference. We can see how, or we're going to see in the next session that I go through, about how the speed of light kind of throw this in the head. And this is going to give us happily to introduce you to some of the ideas of Mr. Albert Einstein. And I thought I'd leave you with one of my favourite quotes of his. When a man sits with a pretty girl for an hour, it seems like a minute. But let him sit on a hot stove for a minute, and it seems longer than an hour. That's relativity. If only it was that simple. And we're going to find out more about that in our next session.